estás?
Well, it's a pleasure to introduce a very dear friend of Alberto, Santiago López de Medrano, who works in the Institute of Mathematics in UNAM in Mexico City. And he's going to teach us a little Spanish today through mathematics. 29 years of topology and geometry, intersections of quadrics.
Okay. So when I get very excited about the theorems, I tend to lower my voice. Not like Alberto. So if that happens, please make signs up there. Okay. So I'm not going to say a few words about Alberto before my talk. All of my talk will be a few words about Alberto. And about Alberto and some of his friends, but mainly about Alberto. Okay, so it all started exactly 29 years ago. It was the seminar, Dynamical Systems Seminar at our institute. First seminar of the year, 1984. And Alberto was talking, and at some point he pointed out a problem in the blackboard, an open problem coming from dynamical systems, and he pointed to me and they said, that's a problem for you to solve. Recently, he confessed he expected me to have the solution for the next Monday.
Exactly.
No, didn't happen. It took me about a year to find out the answer, and a few more years to really write out all the proofs. And this is the question. I'll say a little bit about the question and these sort of conditions, because there are many characters in this story, and it can be a bit confusing. So I'll start by telling something about this before going on with 29 years. So the question comes from dynamical systems, and very simple dynamical systems. Linear dynamical systems in CN. And there was this study by Camacho, Kuiper, Tallis, where they studied the topological classifications of these systems. And as it happens, I'm trying to source the real version. In these systems, there are solutions, two-dimensional in this case. Solutions are classified by the following property. There are some solutions that get close to the origin. There are some in the future and the past approach the origin. And there are some other solutions which stay away from the origin, keep their distance from the origin. And the question was to describe the topology of this set, of this orbit space, this nice solutions. These are not nice in the sense that the orbit space becomes one half or complicated, many other things. But for this part, the space of orbits is very easy, because it is possible to find in each of these, in each of these leaves, there's always a point which is closest to the origin. So there's a section, transversal, there's a subset of Cn which has exactly one point of each orbit, so the orbit space is that. And that orbit space is given by that equation, simple quadratic equation. It's simple quadratic equation, except that it's not holomorphic. There's no, it's not a polynomial in the complex variable C, but it depends on the absolute values. Okay? And well, that was a problem to describe the topology of this set being
The transversal set.
the transversal set.
Mm-hmm.
That would be the topology of the space of this.
It's Z dot I? Is it a dot? Okay, good. My eyesight is going.
Very simple. I can solve this equation too. The geometry is not trivial. Okay, and so I worked on this. So that's one case.
But that only shows how misleading it is to solve equations. That only shows how misleading it is.
So this is one case. Let me call it with the limitation complex. This one. Of course, everything is intersected with the unit sphere. These things being conic. It's enough to consider an intersection with the unit sphere. In the process of solving this problem, I run into three things. First, that I have to consider not only these guys, but the real versions. That is, the intersections of two quadrics in Rn. Intersection of the sphere. Was not enough to consider this, I had to study this, and one had to study also halves of this. Not only the manifolds, but half of these manifolds. Okay. And then, well, after I solved this problem, partially with some restrictions, and then that was enough to solve this problem completely. And I solved this problem also partially, and that happened back in the 80s. Okay, so that's one part. Next chapter of the story is Alberto and me in Brazil, when we hear a talk by Nicolau about his work with Webb about certain deformation spaces of complex varieties, and immediately Alberto told me we can work this out also in our manifolds. And then we worked for a couple of years, and we got some nice results about these manifolds. The main thing is that we got some manifolds and their deformations, but they were new examples of complex, non-algebraic, non-symplectic manifolds coming out of this. They came out of this in which way? Going in projectivizing. Projective space. You projectivize these guys, you get some new manifolds. There are submanifolds of complex projective space. They're not complex submanifolds because they're not given by polymorphic equations, but they are complex manifolds. Okay, so that was another thing. Then Laurent, student of Alberto, extended this to the case where instead of here's a lambda I R and C, what happens if you take the lambda I in Cn, Ck, not only one equation, but many equations. And so he extended our results, but not only he extended his results, he went deeper to study that. Next part of the story is Alberto and Laurent find a relation between these guys and toric varieties. Every time I gave a talk about this subject, somebody in the audience says, well, that's like toric varieties. But it was always a mystery. Yes, it looks like that. And they found how this worked. And then 2002, 2004, Laurent and Alberto and Frederick Bosio, they went deeper into the study, and important for me is that they went deeper into the study of the topological part of the intersection of any number of quadrants. So here we can take any number. And another part of the story has to do with the following. Well, here we have intersection of two quadrics. And it's not any couple of quadrics, even homogeneous. They are simultaneously diagonalized. So at a certain moment, I started looking at more general things like this. With cross terms. Okay. Keeps going. In October 2007, I heard a talk by Samuel Keating. I've told the story many times, but it's a nice story. I was sitting there here listening to Samuel. I couldn't understand a word he was saying, but it was all very strangely familiar. There were these spaces constructed from a simplicial complex. There were the compositions of the homology was computed by doing some strange decompositions. They were all very familiar with everything I had done here, which I will explain a little bit later. And I felt like in a dream. I was in this dream. I was sitting in my house around my table. Around the table there were many people. All the relations within the people, the splittings, the fights, the groups they made, they were exactly like my relatives. But they were not my relatives, I couldn't recognize any of them. Then after a few sessions on Dr. Gifter's couch, I discovered that they were really my relatives. My dream. Okay, so we got some new results, and well, I have something more to say. This all came from what Samuel did, came from another school called toric topology. In this school there were, long story, also about 20 years of work, where they work in a different context, with a different objectives, but they work many of the objects that I had studied here. For 20 years there were these two schools of thought that had in common some objects, had done things about those objects, but we have not been in touch at all. So from there on, that involved many other people we didn't know. A lot of till now we were all Alberto's friends. Now, suddenly there were many people interested in the subject and working, and that got us working more. So we 2011, all this got me to filling up a lot of this, all things I said that were not solved here were solved, particularly this question about non-simultaneously diagonalizable intersections. Well, and it keeps going on. Alberto started with student Yadira, with the student worrying about contact structures. It's an interesting question because these manifolds, the even dimensional ones, are in general not symplectic. They're not symplectic structures. But they started looking for contact structures, and then they asked me about if our manifolds had open book decompositions. And this time it didn't take me a year to answer. I had the answer because we had worked that with Samuel. And then there was the question of what's the topology of the leaf of this open book. And then I had most of the questions. The leaves are these guys, and I had some of the questions, and I worked with some work. I finished this case, and then that was very useful also to consider not only these manifolds but the deformations. It keeps on going. Last December, Yadira and Alberto finally told me we have found the contact structures, but not in our manifolds, in some variations of them. So we have to find out the topology of those. Immediate answer, we have it. These variations really are of this type, and we have the solution. And but in the original manifolds, most of this, not all, but most of this manifold have contact structures. And all the non-diagonal manifolds have contact structures. That was the solution. Also, another interesting part of the story is work by Lupercia and Alberto and Loran, who are constructing. It's not finished, not quite finished. So it's Alberto and Loran related our manifolds with toric varieties. In some cases with toric varieties, but the other cases, that's the idea, as I understand of Lupercia, can be thought of non-commutative deformations of toric varieties. I can say that without blushing. Okay, there are many other things we are working. In dimension 2, what happens in dimension 2 and dimension 3? Dimension 3 is more difficult, but in dimension 2 it's interesting to know all the surfaces with this or more quadrics. We've been looking at other structures, Sasaki manifolds, Sasaki structures and things like that. And finally, I'm starting to looking back at the old manifolds, because here we did a lot about complex structures, but we didn't finish the topology. So I'm trying to look again at the topology. And well, the main objective here is to find the topology of the real projections. So I'm starting with the complex one, but easier. As you see, I've been getting better and better at answering Alberto's questions. But there's a question he asked, I don't know, maybe 1985, about the projective intersection of work. And that's really difficult. That one is really difficult. So I hope that by looking at the projective complex ones, I can start thinking about finally about this unfinished homework I have. Okay, so that's the timeline, and I'm going to tell you a little bit about something more, some more detail. What are the answers? That's in the case of two quadrics, and we have almost complete answer in this case, so I'm going to tell you about this part with more detail. Okay, so what's the question here? We have a function, quadratic, a couple of quadratic forms, nothing more complicated than that. There's a diagonal case, particular important case, diagonal case, where you can diagonalize both quadratic forms simultaneously, but you cannot make this all the time. And the question is, what's the topology of the variety given by f answer 0, of course you intersect with the sphere, and well, one can try to understand also other inverse images. In this case, it's not enough to consider the intersection with the sphere. It could change with the radius of the sphere in topology. It's a different question. But I think the first question about this, guys, is, shouldn't everybody know the answer of this? We have two quadratic equations. For one quadratic form, we know the answer. Everyone knows the answer. Now, let me remember it. Some things you know. So we have one quadratic form. Find its zeros. In this case, you can always assume it's diagonalized. No problem. And then we start asking questions like this. So very simple. This equation is regular outside the origin, or if we consider intersection with the unit sphere, that intersection is regular, if and only if all the ai are different from 0. Non-degenerate form. So you would have of the ai, you would have some of them are positive, some of them are negative. And if you want to study the topology of f inverse of 0, then you have some freedom, because you can move these points, you can perturb these points, and as long as you don't touch the origin in your deformation, you get the same manifold. You have a regular manifold, and you perturb it a little bit, you get a regular manifold, and so there are all these when you change the coefficients without keeping them away from 0, the topology doesn't change. So you can assume this. You can assume that all your manifolds, all your coefficients are 1 or minus 1. That's the same topology. So you have P positive, Q negative. So you have this as the composition M equals Q. And that's all. in this decomposition, the index or the signature, or whatever you want to call it, in this decomposition, it's all the information about the manifold. You know that, you know everything about the topology of the manifold. And it's not difficult to extract information. So you have the sum of P1s, another sum of, let me call it yi's, the ones with negative sign, coordinates, 1 to q. You have this, you have intersection with the unit sphere. Now you do not first year calculus, but high school algebra. You just add up, and this is equivalent to the system. And so the topology is that these coordinates belong to a sphere dimension (3 minus 1), and the other coordinates belong to a sphere. In that case, it's not, the variety is not homeomorphic to a product of spheres. It is a product of spheres. Okay. And then if you ask this epsilon, well, we'll work a little bit more, but it's the same answer. Everything you have to know is contained in this here. Well, so the question is now what to do in the case of 2. Somebody must have done that, I thought, but there was not very much. There's not very much done about this question, and only after solving the first of Alberto's problems, I found out that there was a work by C.C. Wall, Terry Wall, that the study of the topological stability of differentiable functions. He found he had to study exactly this, including the non-diagonal ones. He had done something about it. And before that, there's nothing about that. Maybe one reason is that precisely because this function is, from the point of view of singularities, is quite nice. Finite type. It's, the origin is a singularity, but it's a very nice singularity state. But when you take 2, then it's no longer the case. For example, you take this simple map, the handkerchief folded in 4, it folds the plane twice. This is from the point of view of singularity theory, it's a very degenerate map. Why is it degenerate? Because you have all these are singular points, so you have a line of singular points, and the image of that line of singular points goes like this. It's a fold. It's folding of the line, but it's a line of singular points inside R2. And that's very, very degenerate, because you can make all kinds of small changes. These you can deform in infinitely many different ways. is a singularity of infinite codimension. So in a certain way, this singularity shouldn't happen. One should not find this kind of singularity out there in the world, but they do appear. They do appear a lot. The work of Camacho Corpalis, also studied by Chaperon, they can appear as normal forms of vector fields, as not deformations of non-commutative varieties. They're related to many other things like polytopes, toric varieties, quasi-toric varieties, topological analogs of toric varieties, group actions, etc., arrangements of subspaces. And they also give very interesting examples of complex varieties, as I said, vibrations over toric varieties, invariant varieties in Hopf bifurcations, varieties with special actions, etc. Varieties with special line curvature, Lagrangian, non-formal varieties and planar fibers. And I was with some guy in numerical analysis that used them, and they form part of this other theory of toric topology. Okay, so they do appear, have been studied by him in the last 20 years. Okay, so I want to do the same thing I did there. Now my coefficients AI, BI. I start with a diagonal case. This intersection of the unit sphere, the coefficients, which I keep calling A lambda I. Forget the complex numbers, doesn't matter. And so the coefficient will be points in the plane, and then takes a bit of work, but you can discover what's the condition. The condition to have a regular system, so the origin or in the sphere, is that if you trace all the lines joining the lambda I, the origins should not be in these lines. So the origin condition is the origin is not the convex combination of any pair. It's not enough that they're not zero, that there shouldn't be two lambda i's like this. So the answer is this. The origin is not in the convex hull of the lambda of 2 lambda I. Here the answer is the AI, one AI is not in the convex hull of, sorry, 0 is not in the convex hull of one AI. Fancy way of saying that. Okay, so we have this. And the nice thing is that we can deform continuously the coefficients. As long as we don't break that condition, we get the same manifold. Okay, and that let me give you an idea what can do. The idea is to put together as many coefficients as possible, like in here. For example, we have 4. You have 4 lambda I, and the origin is here. Then, as you can see, you can put these two together without breaking the condition. You try to put these two together, at a certain point there will be a line run from here to here. And the answer then is But you can always do that, and you end up with points in you can put choose special points, roots of unity, for example. So you have a regular polygon with L with L vertices, and then you can put multiplicities. On those coefficients, so you have the composition. The composition of the dimension of the space by assigning from this decomposition you take n1 times this coefficient and times so on, and that's a normal form for a system like such a system of equations. And any other system can be put in this form. If you know this, in principle you know everything about the topology of the manifold. Okay? Here it's this kind of cyclic. Maybe it's cyclic, but you get the same. So it's a cyclic partition of n. Here we have a partition of n. It's also cyclic in the sense that if you change p and q, you get the topology. But there are lots and lots of spaces. That grows linearly with n, the number of cases, this grows exponentially. Okay, so in principle, all the topology of the manifold should be well. In principle, the way it works is as follows. First of all, you have this manifold C. This manifold given by only squares in the variables. Then there's an action of C to the n actions on this manifold C by changing the signs of the coefficients. You take a point in this manifold, you change in any way the signs of the, not the coefficients of the variables, you get another term, the same manifold. So one can take C over C2 to the n, and the quotient turns out to be a polytope. It's quantity C. Really what you do is the quotient of this manifold by this group is just the intersection of the first ortho. The subset with all the coordinates are non-negative. And that's still kind of curved, but it's very easy to straighten it up to make a polytope. So the quotient is always a polytope. And actually from the polytope you can recover everything. You put the polytope here in this space, and then you reflect kaleidoscopes called by Alberto. You reflect in all faces, and you get back your manifold and the action. Once you know the polytope, you know the manifold and the action. It's a simple polytope. I won't describe this for the moment. And let me know. Whoops. So we have this composition. start with the composition. And first case, you have just one. That means the manifold is empty, not interesting. Like they're all on one side, the manifold is empty. And the next interesting case is the L equals 1. L equals 1. We have 3 points. And we have multiplicities. Then I show that in that case, the polytope is a product of simplices. And then for a product of simplices, I could find that the manifold is a product. And in this case, the manifold is a product of three spheres. Only years later, I discovered I could do the same trick. I just write out the equations. At the map, I have three spheres. My simple manipulation. That's it. So in this case, this is. And this next case is the orthogonal case. We have 5 L equals 2. So this is simple, and there's another simple case that can be solved when L equals 2 and everybody is 1. The composition of 5 plus 1 plus 1 plus 1 plus 1. Then it's all very easy because we're in R5. We have 3 equations. That's a surface. And it's easy to see that the corresponding polytope is a pentagon. So you can compute the order characteristic of the manifold surface. The manifold is formed by 32 pentagons. It's the pentagon and its reflection. You know the planes. We have 5 lines, but each line corresponds to where one of the coordinates is 0. So you only have 5 times 16 reflections, and you have 5 vertices. And each vertex has, it's a point where 2 coordinates are 0, so we have this, fill it up, and get in that case, Z is the surface of genus 5. And that's an easy case, and after that, it's not easy at all. Maybe someday somebody will come with an easy proof. Finally, I got this here. These 2 cases are representative of what happens in every case. If when L equals 0, it's empty. When L equals 1, it's a product of 3 spheres. And when L, for general L greater than 1, what you have is a connected sum of product spheres. I've copies. So you get the same answer, but more general. Here, the exponents are as follows. The VI are obtained like this. You take a sum of almost half of the BNIs, that's a BI, and we go around cyclically, and this goes on dimensions of first proof, 1985-6, was using was good only in the case where the manifolds were simply connected of dimension of these 5, because I have to use the H conversions there. And it's only last year 2 years ago that I finished putting up all the cases. You need different proofs with different cases. It's all very baroque, but we have the answer. I'll skip a little bit of that. Next, we have the non-diagonal case. The non-diagonal case can always be put also in normal form. That was known already by Wall in 1980. The normal form is you have a diagonal part, which then one can assume it's in the same form, and then you add terms just like squares of a complex variable. That's a normal form. The manifold is then given by the partition and the number S. You have well-known case if you have S equals 0, then you only have this part, and it's well known that that manifold is the unit tangent bundle of the sphere. Seifert manifold. We finally proved that you get the tangent, unit tangent bundle of the sphere. You get also product of spheres, product of two spheres, and then you get more connected sums of the same kind. And finally, we have all the manifolds. There's a problem in dimension 4 because it needs a special argument, and I'm always claustrophobic in dimension 2 and 4. But I think it's also topologically it's true, but differentially it's true. So we have a complete description of all the intersection of homogeneous, real, generic quadrics in Rn. Okay, so what about time? Well, I'll go fast with the rest. Then, okay, so this means there are. I'll go fast with this. It takes different things for different cases, and there are different constructions. Getting up, making S go up, making one of the ends go up. You start with the lower manifolds are always very, very connected, highly connected up to the middle dimension, and those are easy to consider. And then you go up by induction, and other operations involve cutting the polygon, doing combinatorial operations like cutting the polygon. Okay, so everything can be done with equations. I won't bother you with that. Geometrically, the good thing is that adding one non-diagonal case is like taking a double covering of the sphere, ramified over the original manifold. The other one is an open loop, and when you cut the polytope, if it's not very deep, the cut doesn't go very deep. The manifold is connected sum of two copies of C plus a number of handles. And probably the idea is that these three operations preserve connected sums, so we can go looking. Start with the lower manifold of work up. It's messy. Okay, then mention the half varieties. We'll consider only half of the manifold, and they can also be described. I'll mention only briefly. The idea is that so here what you have is a composition. And one of these guys is marked because it's the one where we're not taking the whole manifold, but only one of the coordinates here has to be negative. And so it's half of both manifolds in the same description instead of a product of two. Instead of the product of three, for one of the three spheres, you only take one hemisphere. And also in all the other compositions, instead of one of the manifolds, you get one of the spheres. Some of the spheres, you only take a hemisphere. So you get connected zones along the boundary. There's just a very complicated case, but the main thing here is that you can see everything from the diagram, from the composition. We have this, and you have the first cases. You get the boundary is the manifold when you take that coefficient. That first coordinate equals 0. But then what happens if one of the ni is 1? If one of the ni is 1, and you want to know what's your manifold, it becomes complicated because what's the boundary of the manifold? The boundary of the manifold is when you take that coordinate equals 0. You take this coordinate equals 0, that's fine, you still have a good system, except that now these two that were different, that were separated, now can be joined into a single one. So all the complication from this case you can read from the diagram. And when it's 3, it goes down to, from 3 to 1, it's worse. So there are some cases with some ambiguity. Okay, but it's not very complicated. Most of the cases are just like surfaces. You can think of those connected zones just like surfaces, and this case is just a surfaces with boundary. Some of them are just connected zones of fathom disks, or other are fathom disks with handles. But it's most of them are interesting, are easily described. Okay, and they're interesting because they're the pages of the book of composition, and hopefully they're related to the complex structures, and they're related also to the inverse image of the other points. So in that case, I'll say it very briefly. The main result is that these inverse images, you have to know when you get the regular inverse images, these inverse images are really just like this half manifold. And you have to know where to. What you have to know now is the relation with the T, the inverse image of T, which is also the point on R2, and what's the relation with this point with all the other ones. And well, there's a regularity condition. Let's keep on this. example, I just give one case. Okay. So the main thing is the following. Taking f inverse of t is taken a half manifold, but where you have not only the li's, but it's by t. And the condition is where is the t? You can put it in the circle again. If it's far, when it's a bad point, it's when this line crosses one of the diagonals. When it's singular value, when it crosses the manifolds. If not, then you incorporate this to the configuration t, and it may happen that inserting t in this configuration might increase the number of points, the genus I would say of the manifold. So it takes some time, but the final answer is actually very simple. You just have to draw your diagram like this and put your t, and you know what the answer is. And well, one can compare with the holomorphic case. In this case, we don't have a vibration. At most, we would have a vibration of every on top of every little piece, complement of all the diagonals. And the fibers are sometimes bouquets of spheres, sometimes not. Only they become bouquets of spheres after suspension. So one or two suspension become bouquets of spheres. The main problem here is what happens when you have not two, but more quadratic equations. Okay, let's go to next case 3. And that's very difficult. The main problem is there's no normal form. You cannot get a normal form. Getting a normal form in general would be more or less equivalent to classifying all polytopes, or all simple polytopes, and that seems out of question. All the concepts, ideas work, but there's no normal form. The topological results are false. It's not the case that it's always a product of sums of products of connected sums of spheres. There are many more complicated examples. Some found by Bose and Bersoman. Some were known in the other school from competition. Knew about that. Somehow the competition was interested in finding ugly examples. One said, I have found this horrible example. The topology can be this horrible, and then the next one, 2 months later, found one with a worse example. And somehow they missed the simple ones that we knew on this side. On the other hand, we were kind of naive. We thought that everything would be simple, but that allows us to find these results. And the work with Sam Gittler, what we did is using Bose's Merselman ideas to find large families of these manifolds with any number of quadrants, intersection of any number of quadrants, large family which are just as simple as the ones I mentioned here. And we will, here this has been going on for 29 years with some periods with were not advanced, but in the last year everything has been advancing very fast, and we have This is due to the work of Bossi and Merseman, to this construction by Hitler, which is called generalized moment angle complexes. All the guys you've seen here are a particular example of these moment angle complexes, and they have very general terms about them, about the algebraic topology. And I have to mention also that because it's very important in this last part of the work. Okay, so that's it. Thank you.
Questions? Okay, let's.
The way to organize the project is also using cover design. Have you seen how which cover design classes?
There are these. They're all very trivial in that sense. The manifold C, they are complete intersections, so they're stably parallelizable. But not only this. You can construct problems. You have one of these manifolds. You add one new variable. You get a manifold one dimension higher, and then you take half of that dimension. So it's very easy to find that. They're always bound parallelizable. Then there are the quotients, projective quotients, except for no equation where you get a complex projective space. They're always bound. In that sense, it's kind of non-exotic business. You get lots of spheres, but they're always standard spheres. The four manifolds you get, well, I'm pretty sure that they're standard products. So they're not so. The actions, well, the manifolds with the actions, the complex action has a torus. The complex manifold has a torus action. The real manifold has a C to the n action. The manifold with those are more complicated. There are other quotients that are like rhetoric varieties, and those are more complicated for the end of the probabilism. For example, some of them give a list of generators for a complex probabilism.
Perhaps you should mention that every stable parallelizable manifold compact is the intersection of quadrics.
Yeah, that's...
No, because maybe you're thinking just a few examples where every manifold is like that. Can you say something?
No, but just... In quadrics, I mean not non-homogeneous quadrics.
Non-homogeneous quadrics.
With homogeneous
Quadratic.
quadrics, there's also some symmetry. But,
No, quadratic coefficient.
with quadratic equations, having linear term and constant term. Constant term is more or less handled.
Yeah, with linear
And,
terms.
one next step will be to consider just any quadratic function, linear and constant term.
So any manifold is a
But any manifold which is
stable parallelizable.
stably parallelizable is an intersection of quadrics with non-homogeneous quadrics. That's a theorem by Michel Herman that we rediscovered 30 years later. It shows Herman's third cycle thesis unpublished at this theorem. About 10 years ago. Okay, so we're getting there.
Other questions? Okay, let's Thanks.